Have you ever stopped to think about how a self-driving car actually sees the road? Or how some apps on your phone can magically place a new sofa right in your living room? It all boils down to this incredible process, teaching a computer to see in 3D. So let's just dive right in and unpack how these machines turn flat, ordinary photos into a rich, three-dimensional world. I mean, just look at this entire super detailed 3D scene, all of its depth, its texture, its structure, was built from nothing more than a simple video you could take with your phone. It honestly feels like magic, right? But it's actually this brilliant mix of some pretty simple math and some very clever geometry, just scaled up thousands and thousands of times. And the whole thing starts incredibly small. So that's the big question, isn't it? How in the world does a computer go from just a bunch of flat 2D pictures to actually understanding the shape, the distance, and the layout of the real world? Well, as you're about to see, this whole amazing journey begins with something tiny, a single pixel. To solve this massive 3D puzzle, a computer has to start with the smallest possible piece. You can think of it like it's playing a game of spot the difference, but on a microscopic level. It's trying to match these tiny little blocks of pixels between two different pictures that were taken from slightly different angles. Okay, so here's the problem boiled down to its absolute simplest form. We've got this little 2x2 block of pixels from one camera's point of view. The computer's entire job right now is to find that exact same block inside a bigger search area from a second picture. Now, each number you see here just represents the brightness of that pixel. So how does it know for sure when it's found the perfect match? Well, it uses a simple but really powerful method called the sum of square differences, or SSD for short. The best way to think about it is like a scoring system in a game. For every single possible position it checks, it calculates a different score. And the goal is super simple. Find the spot with the absolute lowest score, because, the lowest score means it's the best possible match.
And the process itself? It's really just basic arithmetic, which is wild. So first, you slide the small block over a potential spot. Then, for each pixel that's overlapping, you just subtract its brightness value from its partner. And finally, this is the key part. You square all those little differences, and then you add them all up. Squaring them is the secret sauce here. It gets rid of any negative numbers, and it really penalizes the bigger differences, which makes the best match stand out that much more. That final number, that's your score.
And what's so cool here is we can see the results of that game. The winning match has a tiny score of just 4. I mean, look at the other possible positions. They give a much higher score, like 37 or even 112. It's a no-brainer for the computer. The lowest score wins, so it knows with absolute certainty this is the match. So, here's the crucial point. The computer doesn't just do this once. It repeats this simple little matching game for thousands, even millions of pixels across the two images. And when it does that, something amazing starts to happen. All of those individual little matches start coming together to give the computer its very first glimpse of depth. And this right here, this is the result. It's called a disparity map. Now, it might look a little ghostly, I know, but this is a huge leap forward. In this image, the brightness level is actually telling us the distance. The brighter an object is, like that chair in the foreground, the closer it is to us. The darker areas, they're farther away. The computer is literally starting to see in 3D. Of course, the first pass isn't always perfect, but by just tweaking a few of the algorithm's settings, like changing the size of that pixel block it's searching for, we can get a much cleaner, more detailed, and a way more accurate result. You can really see how much clearer all the objects in the room have become here. It just pops. Okay, this is really cool, but a bright pixel isn't exactly a measurement a robot can use to navigate, right? So that brings us to the next big question. How do we get from this sort of abstract map of disparity values to a concrete, real-world distance measured in something we can actually use, like meter? The answer is right here in this beautiful little formula. You could think of this equation as the bridge, the translator that connects the computer's world of pixels to our physical world. It just uses a few key pieces of info about the cameras to convert that pixel shift, that disparity, into an actual measurable distance. So let's plug in some real numbers and see how this actually works. Okay, so we know the distance between our two cameras, that's the baseline, is 0.2 meters. We also know the camera's focal length. The disparity map we just made tells us a specific pixel on that building shifted by about 5.375 pixels. You plug those numbers into the formula and boom, the computer calculates that the object is 26.9 meters away. Just like that. Now, all of that works perfectly if your two cameras are lined up just so, perfectly parallel. But in the real world, say on a moving robot or a drone, things are never that perfect. So what happens when the camera views are a little bit rotated or misaligned? Well, that simple pixel matching gets totally confused. We're going to need smarter math. So the solution is to move beyond just looking at pixel brightness and start using geometry. We calculate something called the fundamental matrix. It sounds complicated, but it's basically just a mathematical description of the exact geometric relationship between the two camera views. It acts like a guide that can correct for all those real-world imperfections. And this is what happens when you don't. This is the result from a more basic approach. It's trying to find the corresponding lines between the two images, but because it's so sensitive to even the tiniest errors, the result is just this: a messy, incorrect jumble. This is basically visual gibberish for a computer. But now, look at this. By using a much smarter, normalized version of that same algorithm, the results are dramatically better. Bam! The lines are clean, they're parallel, and they accurately map the geometry of the scene. This is the kind of solid, robust matching we need to build a reliable 3D model. Okay, we've matched pixels to get depth, and we've used geometry to make sure it's robust. So now it's time for the final step: putting all of these building blocks together and scaling everything up from just 2 photos to hundreds to get that incredible result we saw at the very beginning. This huge, unifying process is called structure from motion, or SFM. And it's a perfect name, really, because it does 2 amazing things at the exact same time. It reconstructs the 3D structure of all the points in the scene, and it also figures out the camera's motion as it moved through that scene. And this brings us right back to where we started, full circle. On the left, a single flat frame from a regular video, and on the right, the final output of structure from motion. It's a complete, navigable 3D point cloud of the entire environment, all built by just applying those core ideas of matching and geometry over and over and over again. So we've gone on a pretty wild journey, from a few individual pixels all the way to a full 3D perception of the world. And this isn't just some neat academic exercise. This technology is fundamentally changing how machines interact with and understand our environment. I mean, just think about the path we took, right? We started with the simplest thing imaginable: basic math on tiny squares of color. We scaled that up into a depth map. Then we used smarter geometry to handle all the messiness of the real world. And finally, we put it all together to build an entire 3D world from scratch. From robotics and self-driving cars to augmented reality and even preserving historical sites, the ability for a machine to truly perceive depth is absolutely revolutionary. And it leaves us with a really fascinating final thought. If machines can already reconstruct our world in this much detail, what will they be able to see, understand, and do tomorrow?